You can't see it, you can't touch it. But right now, there's an invisible force making it possible for you to even watch this. And, it's the same force that lets doctors see inside our bodies and helps scientists push the absolute boundaries of physics. So today, we're going to make the invisible visible. We're going to explore the incredible power of magnetic fields.
So that right there presents a fascinating puzzle, doesn't it? If you can't even see the very force you're trying to control, how on earth do you build anything with it? I mean, how do you design something as complex as an MRI machine or the next generation of computer memory? Well, stick around because we are about to find out. All right, here's the plan. First up, we'll meet the invisible architect. That's the tech that lets us see and control these fields. Then we'll take a journey through its amazing applications, from giving us a window right into the human body to powering our digital lives and even pushing the frontiers of science itself. And we'll wrap it all up by looking at the true power of being able to predict the future, well, at least when it comes to magnetism. Okay, let's dive into our first concept, the invisible architect. This is where we learn how to see the unseeable. The key to all of this is something called magnetic field simulation. Now, the best way to think about it is like a digital sandbox for magnetism. Instead of building a real, multi-million-dollar MRI machine, engineers can build a perfect virtual replica right on a computer. From there, they can run countless tests, see exactly how the magnetic fields are going to behave, and totally perfect the design, all before a single screw is turned in the real world.
This slide really just nails the difference. I mean, it is a total game changer. In the past, innovation was a huge gamble. You'd spend months, maybe millions, building a physical prototype, only to find out it had a critical flaw. You just have to scrap it and start all over again. But simulation? It changes the whole game. It's like having infinite do-overs. You can test thousands of designs in a single day, find that one perfect configuration, and only then commit to building it in the real world. It's really the difference between navigating with a treasure map versus just wandering around in the dark. So, now that we kind of get the how, let's explore the what. And honestly, one of the most incredible applications is in medicine, where simulation gives us this non-invasive window into the human body. Just take a look at these technologies. From the high-field MRIs that give doctors those crystal-clear images of your brain, to the LINAC MR systems that can target a tumor with a radiation beam while literally tracking its movement in real time, none of this would be possible without simulation. The magnetic fields they use have to be controlled with just mind-boggling precision. And the only way to get that kind of precision is by designing and perfecting them in a virtual environment first. And the takeaway here is simple, but it's also incredibly profound. These are not just some abstract computer models. No, this is technology that translates directly into better healthcare. We're talking safer medical scans, more effective cancer treatments, and ultimately, it saves lives. Okay, so from saving lives, let's switch gears to saving data. Simulation isn't just revolutionizing medicine, it's also the driving force behind our constant quest for smaller, faster, and more powerful electronics. Let's think about the humble hard drive for a second. To cram more and more of your photos and videos into the same tiny space, engineers are using this technique called microwave-assisted magnetic recording, or MAR. And to make it work, first they have to simulate how materials behave at the atomic level. Then they simulate that crucial moment of flipping the magnetic state of a tiny particle, which is how you write a 1 or a 0. It's only by running millions of these virtual tests that they can design a physical hard drive that's both massive in capacity and incredibly reliable. And AMMR is just one example. Simulation is unlocking a whole range of futuristic tech. Can you imagine racetrack memory, where data literally zips around a nanowire at incredible speeds, or tiny spintronic oscillators that could power a whole new generation of wireless communication? Look, this isn't science fiction. These are concepts being actively designed and perfected in virtual labs as we speak. All right, so from the practical stuff we use today, let's take a leap to the scientific frontiers of tomorrow. What happens when we use simulation not just to improve the tech we have, but to invent entirely new kinds of technology? This is where things get truly mind-bending. Right here, we're moving beyond engineering products to simulating the very fabric of reality itself. We're using these virtual worlds to tackle some of the biggest challenges in all of science, like creating clean, limitless energy and understanding the fundamental forces that govern the entire cosmos. I mean, just think about what we're looking at here. Scientists are simulating field-reversed configurations, which is basically a complex magnetic bottle, designed to hold the star on Earth and unlock the dream of fusion energy. They're designing the superconducting magnets for the next Large Hadron Collider. They're even using magnetic fields to levitate objects, creating little pockets of zero gravity to test equipment for space missions without ever having to leave the ground. This is truly the bleeding edge of science. All of these incredible examples, from medicine to data storage to fusion energy, they all bring us to our final and maybe most crucial point: the power of prediction. So what's the ultimate benefit of being able to see and control these invisible worlds? So why does all of this matter so much? Because simulation is a universal catalyst for progress. It makes innovation faster, it makes it cheaper, and it makes it safer. It lets us tackle problems like creating fusion energy that would be completely impossible to solve through physical trial and error alone. Ultimately, it lets us optimize the world around us and just push the very boundaries of what we thought was possible. You know, it really all boils down to this one powerful idea. Simulation gives us the power to test, to refine, and to perfect our most ambitious ideas in a virtual world before we ever have to commit to building them in the real one. It is the ultimate bridge between our imagination and reality. And that leaves us with a really tantalizing final question. Today, we've pretty much mastered the simulation of magnetism. But as our computers get more and more powerful, what other invisible worlds are we going to unlock? The bizarre realm of quantum mechanics, the complex folding of proteins, maybe even the fabric of space-time itself? The possibilities, well, they're as limitless as our own curiosity. Thanks for joining us.